Hello friends, today I'm going to talk about renal physiology. Okay, I will going very brief and okay, let me share my screen. Fine. So what we know up till now, if I've gone through, I will request you to go through my renal embryology video, okay, in the playlist. So you'll be able to understand what is a nephron like. Okay, a nephron is made of renal corpuscle. What is a renal corpuscle? Renal corpuscle uh, is Bowman space. It's the Bowman space. Okay, and what is known as, let me change the color. Change the color, and what is known as this glomerulus. So 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 this is what is known as the afferent arteriole. Okay, this is known as the afferent arteriole. This goes to form a glomerulus, which is a capillary tuft, and from which blood is drained out by efferent arteriole. What really happens in efferent arteriole is the thickness or the width of an efferent arteriole is much wider than an efferent arteriole. So what does it happen? That means there will be a pressure generated at the capsular level, at the glomerular capillary, not capsular, glomerular capillary level within the Bowman's capsule, that will drive materials inside this Bowman space, or the glomerulus. Okay, the Bowman space. Now let me draw the picture again, like this. Okay, wait a minute. So what do we know? There's a nephron. Nephron is the functional unit of the kidney. There are about 1.2 million nephrons in each kidney. If we have two kidneys, we have obviously 2.4. And that will vary obviously with renal agenesis and other problems. But roughly this is it. Now, what really happens in I will show you the diagram. Okay, just a minute. Just give me some time to take it up. Okay. So as far as we know, up till now, we have glomerulus and we have Bowman's capsule. Okay, this forms what is known as a part of the renal corpuscle. The remainder part of the nephron will be the proximal convoluted tubule. Okay, the proximal convoluted tubule. That will be a lot of convolution over here. So that's called proximal convoluted tubule. Then the loop of the Henle goes up, and then it will form a distal convoluted tubule and ultimately drains into the collecting duct. So this is a collecting duct. The collecting duct finally opens up into the pelvis. Okay, so there will lot of nephrons, lot of collecting. The collecting ducts opening up into this. Lot of the nephrons opening up into this collecting duct, and ultimately collecting duct will go and discharge all the effluent, the urine, into the pelvis. So let me tell you, okay, is what are the layers of the Bowman's space? This is known as the Bowman's capsule. Okay, so Bowman's capsule. So there will be this is known as a capillary endothelium. So the endothelial cells will have what is known as the this is the endothelial cells. Okay, this is on the capillary side. Okay, so this is a Bowman's capsule. This is the Bowman's capsule side. Inside the Bowman's capsule, this is the outside Bowman capsule, and this layer will be. I will come into this trilaminar membrane. I will come into this. Wait a minute. Let me talk about endothelial cells. Endothelial cells will have tiny slits, okay, tiny channels within them, through which some material will escape from the blood in the capillaries by effect of the glomerular filtration pressure. But they need to be less than 100 nanometer in diameter to pass freely, that is glomerular filtration, filtered into the Bowman space. Okay, so this is the first, can say the first layer. Okay, the first layer of resistance against passage of materials filtered from the glomerulus into the Bowman's space. Now we have a Bowman's capsule membrane, which is a trilaminar membrane. That's known as the glomerular basement membrane. It's called a glomerular basement membrane. It is a tri-layer membrane. The middle part will contain what is known as type 4 mm, uh, type 4 collagen and laminin. Okay, this is a very tough layer. Okay, it doesn't allow much materials to pass from the your blood side into the glomerulus. Okay, but we'll also have two other layers, the outer layer and the inner layer. This is called the outer external, and this is called the internal. All these are made of proteoglycans. This is the outer layer and the inner layer made of proteoglycans called heparin sulfate, and this is have a negative charge. These have a negative charge. Okay. Now, suppose this is the bone, this is the glomerulus, this is a capillary tuft. This is the only thing and only instance in the body where there is a capillary. There is an artery which is feeding it, known as the afferent arteriole, and an artery which is taking the blood out. It's known as the efferent arteriole. Okay. So otherwise, you have an artery, glomerulus, and an efferent arteriole. This is the only thing which is different from it. Okay, fine. Now, as we know, so we can jolly well understand that this is a as you can understand, this is three layers. So any charged particle like albumin, like proteins which have negative charge will be repelled by the negative charge of the outer layer of the glomerular basement membrane. So it cannot go inside because there's a charge characteristics. But only sodium, potassium, all these minerals. Then we have all these minerals which have a positive charge. They will be able to go through this because of the charge effect of the outer and the inner membrane. Now, inside this, we will have what is known as the glomerular layer, which will have a visceral layer. This is the visceral layer, which will consist of what is known as the podocytes. Podocytes are basically cells which are having food processes. So this is one podocyte, this is one podocyte. And in the meantime, you will have slits. So there will be some channel, like two houses in between, there is an alley. So like that. Again, there will be some protein gates, which will prevent some of the 100 nanometers positively charged ions which are going to pass through this area. So very less amount of electrolytes can pass, or materials can pass through this layer. Up to this is okay, isn't it? So this is, as you know, so it passes through this capillary endothelial cells, outer layer of the capillary of the glomerular basement membrane, which I said is negatively charged. The intermediate layer, which is having a lot of laminin and tough structures, and the inner layer, which is again negatively charged because heparin sulfate goes in between the podocytes, and there is a slit, and there is a protein gates, and then they pass inside and come into this glomerular space. Now there will be some forces which will try to let these materials come inside, which is known as the glomerular capillary hydrostatic pressure. Okay, which I think is around 60 millimeter mercury. But there are some pressures which will prevent these substances which is acting from inside outwards. So one is known as the colloidal osmotic pressure, which is, as I said, all these proteins which are negatively charged, which are repelled. So we try to draw the fluid outside. So it will prevent the fluid to go inside in the glomerular space from the capillaries. So it's a colloidal osmotic pressure is something what? It's something around 25, I think. It's around 20, 25. But remember, there's another factor, another force, which is the within this glomerular hydrostatic pressure, or the base of this thing. It's called the Bowman's space hydrostatic pressure. I'm very sorry. This is the glomerulus. This is the Bowman's space. So this is Bowman's hydrostatic pressure. Think it to be a funnel. What's a funnel? Funnel is this. It's a narrow neck. It goes down. Just think it to be the proximal convoluted tube. So any fluid, any materials is coming inside. If suppose there is some amount of obstruction, some amount of sluggish flow outlet. So because it is a wide outlet, it's a inlet is a low outlet. So there will be something like an overflow of the funnel. So there will be some back pressure changes, which is known as the glomerular. I'm sorry, I'm saying the same mistake over and over again. It's known as the uh, Bowman space hydrostatic pressure. So it's around 15. So there will be a net filtration pressure, which will drive this glomerular filtrate across the glomerulus into the Bowman space. This is known as the glomerular filtration. Now, glomerular filtration rate is about 120, it's approximately 120 ml per minute, or about 180 liters per day. Now, what does it depend on? It depends on this net pressure, this net filtration pressure, which I said. Net filtration pressure is glomerular filtration pressure minus the sum of the colloidal osmotic pressure and the Bowman space hydrostatic pressure. Okay. So it will drive the fluid inside. Another two factors, there's something called the Kp or the coefficient ratio, which is also dependent, on which the glomerular filtration rate also depends. It depends upon the thickness and the permeability of this glomerular basement membrane, which can be altered. It can be thickened in case of inflammation with diabetes mellitus, and the surface area may be, suppose the permeability is being lost with glomerulonephritis, and the surface area will be shrunken because of thickness in case of diabetes mellitus. So these are all the factors which can also affect the glomerular filtration. Okay. So up to this, we know what is glomerular filtration rate, filtration, and the effect of the renal corpuscle, which is made of the glomerulus, afferent arteriole, that is draining in and draining outside the glomerulus, and also what did I say? What did I say? Also a part of it is, and I talked about. Let me erase all these things up for you. So what? So that's very important. You can understand that this is very important. Okay, this is very important. Just hang on for a second. So friends, I think we will take the next class. We'll take the next class to talk about what is proximal convoluted tube. Okay.